Hello students, in this video we'll discuss geodesic triangles. Let's be given geodesic polar coordinates. And 3 points. A, B, and C on a surface S. By orienting the surface in the correct fashion, I can assume that A is the origin in polar coordinates. Okay, great. And then I'm going to choose the polar angle in a moment here after I connect these points. Connect A, B, and C with geodesics. Okay. And if we do this, we'll have a geodesic triangle. This will give us what's known as a geodesic triangle. Okay. So let's take a look over here. So here's my point A. Here's my point B. And here's my point C. I'm going to connect these with geodesics. The geodesic over there. There's a geodesic over there. And then here's the geodesic over here. Okay, so there's my geodesic triangle. And I have angles inside here. There's angle alpha, there's angle gamma, and there's angle beta. And I'm going to choose the polar axis to align with the tangent vector. So V aligns with the tangent vector at the point A, right? And then if that's the case, what I have over here is that this polar arc over here, so then we have 3 sides of this triangle, right? So this side over here is going to correspond to theta is alpha, and then this side over here is going to correspond to theta equals 0. So in other words, those 2 sides of the triangle are level sets with respect to theta in polar coordinates, and geodesic polar coordinates. And then this final curve over here, we don't know much about it. I'm just going to call it gamma, which depends on theta. And then this gamma of theta is r geodesic of some function f of theta, which we know nothing about, and theta, where theta goes between 0 and alpha over here. So theta goes between 0 and alpha. Beautiful. Okay. And now I need to make up some differential notation. So what would the geodesic equations be for these equations over here? So the geodesic equation would be r double dot, because I know the coefficient of r is what? The coefficient of r is e, and e is 1 in geodesic polar coordinates. And then the f is 0, and then the g is going to be, the g is going to be 1, but there's no change in theta over there, so that's going to be a different geodesic equation, right? And so that's going to be r double dot is 1/2 gr, and then theta dot quantity squared, okay? Now here the dots are with respect to arc length parameter, right? So dot is really a d by ds derivative. And what I'd like to do is I'd like to use prime to denote a d by theta derivative. Okay, that's the notion we're going to use. And one other bit over here, we're going to lambda be ds d theta over there, right? Or d theta ds. Ds d theta. Good. Okay? Because what is this thing over here? This is d theta ds, right? So this is a lambda to the -2 over there, right? So that's my arc length parameter. So with this over here, this becomes what? This lambda, this theta dot squared over here becomes what? This theta dot squared is really d theta ds. That's a lambda to the -2. Okay? And so now what I like to do is I know what r is over here. We can do the derivatives of r in terms of f of theta, right? And so what's going to happen over here? So what we know, so r dot will be what? So r single dot would be if I do the chain rule, instead of doing an s derivative, I can do a theta derivative, right? So this is dr ds is really what? Well, that's my f of theta, right? That's my r component on the curve. So my r is really f here, right? Dr ds is really dr, it's really df d theta, right? So I can write this as a df d theta ds, and d theta ds is a negative lambda to the negative 1, right? So it says that an s derivative is a 1 over lambda, a theta derivative over here, right? So if I do a second s derivative, so this implies that r double dot is what? R double dot is going to be a 1 over lambda, then a theta derivative of a 1 over lambda, and then a theta derivative of f. Like that. And so this will be what? This is going to give us what? So this implies that, well, I know that r double dot is this thing over here, so hence 1/2 gr lambda to the negative 2 is going to be equal to what? It's going to be equal to lambda to the negative 2 f double prime of theta. Okay? And then I have to do a theta derivative of this thing over here, so that's going to be a negative lambda prime over theta cubed f single prime of theta. And so now my relationship is the following. I can cancel out the lambda to the negative 2, and we can conclude this. We can conclude that f double prime of theta minus lambda prime over lambda, f prime of theta is equal to 1/2 of gr. Okay? That's beautiful. That gives me a differential relationship for gr, right? Now what I'm going to do is I'm going to let this function, I'm going to define an angle over here. This is going to be my angle over here, psi. Okay? So what is psi? Psi is the angle between gamma dot and sigma r, or gr. So psi over here is the angle between r, geo, r, and gamma dot. Now both those vectors are unit vectors because the e is equal to 1, and gamma is, and this is an arc length parameter, right? So those are both unit vectors. So what's the cosine of theta? The cosine of psi, rather. The cosine of psi is going to be what? It's going to be r geo r, r geo r, dot what? Dot the derivative of gamma with respect to this thing. So that's going to be a 1 over lambda. Theta derivatives of everything, right? So 1 over lambda, and then r geo r. Plus r geo theta. And then, of course, f prime of theta over here, right? F prime of theta. And then plus r geo theta. Like that. Beautiful. Of course, these things are perpendicular to each other, so I just get a f prime over lambda, right? So this is just going to be f prime over lambda. Beautiful. And then similarly, what we can see by the same calculation with the cross product over here, so the sine of psi is going to be what? I'm just going to change this to a cross product. If I change this to a cross product, this first term is going to vanish. I'm just going to have a 1 over lambda times the length of this thing over here. And the length of that normal vector, so the length of the normal vector is the square root of EG, is the square root of EG minus f squared. So that's just the square root of g, right? So this is just going to be 1 over lambda, so it's going to be g, root g rather, over square root lambda over lambda, like that. Beautiful. Get that relationship over there. Okay? Just because I'm going to have this 1 over lambda, and then the cross product of those things, the length of the cross product is going to give me a square root of g. Okay? Great. Okay. Now let me take this equation over here and differentiate it. So if I differentiate this equation over here, what do we get? These two equations together imply that the cosine, if I imply that f prime over lambda prime is the cosine, which is negative sine psi prime, right? And so that's going to be negative psi prime, and then the square root of g, and then over lambda, right? Now, if I take this over here and expand it out, what does it become? This expression over here becomes what? This expression becomes a lambda f double prime minus what? Minus lambda prime f prime over what? Over lambda squared. Beautiful. And now, of course, I can cancel out one of these lambdas over here. So if I cancel out one of the lambdas in this equation over here, let's cancel out this lambda over here, and then this lambda over here. So this becomes f prime. So in other words, we have f prime minus lambda prime over this is the square root of g lambda prime, right? So hence, this implies what? This implies lambda f double prime. Just kidding. It implies that f double prime minus lambda prime over lambda f prime is equal to what? Is equal to negative psi prime square root g. But we know what? So we know that over here, we know that f double prime minus lambda prime over lambda f prime is 1/2 gr. So this is 1/2 gr. And what does that tell me? That tells me that this psi prime is negative the r derivative of the square root of g. Beautiful. Okay? So psi prime is negative the r derivative of the square root of g. Okay? Now, we know what the derivatives of the square root of g relate to curvature, right? And so what I'm going to do is the following. I'm going to integrate over that triangle t. So this is my triangle t. It's a double integral. Of what? Of just the curvature, of the Gaussian curvature. dA. Let's figure out what this is going to be. Well, this is going to be the integral. Theta goes between 0 and alpha. R goes between 0 and f of theta. And let's remember what the curvature was. The curvature was what? Was negative 1 over root g, the second r derivative of root g. And then what's dA? Then dA over here, dA is going to be square root g dr d theta, right? So the root g and the square root g over there are going to cancel out, and so I'm just going to have the negative of the second derivative of r, right? So I can do one r derivative. So if I integrate this, this is going to be negative 2 derivatives of root g dr d theta. Good? And so what will we get? We're going to get the integral from 0 to alpha. Now if I do one r derivative, I'm just going to have negative the r derivative of g. By doing one r integral over here, I get rid of one r derivative, and then what will be left over is the antiderivative is negative d by dr of root g, which is just psi prime, right? So that's just going to be psi prime evaluated from what to what? Or just negative, let's do it like this. It's going to be negative d by dr of root g evaluated from 0 up to f of theta. Now this relationship is only valid on f of theta, right? So in other words, this expression, this equation over here is valid for r equals f of theta. Right? So in other words, that differential equation is satisfied on that curve. Okay, and then I have a d theta. So this becomes what? This becomes the integral from 0 to alpha. And then when I plug in f of theta, I just get what? I just get psi prime of theta. When I plug in 0, I get 1 because I know root g, it looks like what? Root g is locally r plus negative kappa, negative curvature over 3, r squared, r cubed, right? So if I do the first derivative, I get a 1, so I get a plus 1 over here, d theta. And so this is what? This is alpha when I integrate the 1. And then psi prime of alpha minus psi of 0 plus psi of alpha minus psi of 0, right? So that allows us to get the following relationship for this geodesic triangle. So what's our main conclusion from this? So what is psi of alpha? So if I look at this over here, so this angle over here is psi of 0, and this angle over here is psi of alpha, right? Good. And so our conclusion, therefore, is that the double integral over this geodesic triangle of the Gaussian curvature dA is exactly equal to what? Is exactly equal to alpha plus psi of alpha minus psi of 0, right? Okay, so this is alpha. Now psi of alpha is the same as the angle gamma, right? So that's the same as the angle gamma plus gamma. And then what's this psi of 0 over here? Well, that's going to be what? It's going to be pi minus beta, right? So that's going to be minus pi minus beta. And so our conclusion, if we add this all together, is that the total integral of the Gaussian curvature over that geodesic triangle is alpha plus beta plus gamma, which is what you sort of expect the curvature to integrate to, but minus this factor of pi, right? And that gives us a first version of what is known as the Gauss-Bonnet. So this is a simplified version of the Gauss-Bonnet. So this is a first version of Gauss-Bonnet, which we will discuss in further videos. So I'll scoot over so you can see the main result and say thank you very much.